Now going to question 13. Here the prompt is asking us which finding, if true, would support the researcher's hypothesis. And what's the hypothesis? Under normal atmospheric pressure at Earth's surface, the water molecules form a network stabilized by hydrogen bonds between molecules. Extreme high pressure, such as can be found in deep ocean waters, destabilizes these bonds and compresses water structure, allowing water molecules within organisms to permeate proteins and impede crucial functions. Yet, deep-sea organisms have adapted to extreme pressure. Studies have found a positive correlation between the depths that various whatevers inhabit and concentrations of a compound in their muscle tissues, which has led a team of researchers to hypothesize that TMAO reduces water's compressibility. So now, after all that, what is the researcher's hypothesis? It's there at the end. It's the idea that the TMAO is reducing water's compressibility. Just to review a little bit, there's this research being done, and deep sea organisms have somehow adapted to extreme water pressure, and scientists studying that found a correlation between the depths and this compound called TMAO. And then, like I said, the hypothesis is that TMAO reduces the compressibility of water. In other words, it resists the high water pressure. So let's look at the answers. A says, water molecules are found to be impervious to TMAO, even when the water's configuration has been distorted by high pressure. Well, we don't want it to be impervious to TMAO because the idea was that the TMAO is helping to resist the high pressure. So to be impervious to TMAO, that's like saying the TMAO can't affect it, which is kind of the opposite of what we're saying. We're saying that the TMAO helps the water molecules. B, examination of TMAO's molecular structure shows that TMAO molecules retain their shape even as pressure increases. That actually fits because the hypothesis was that the TMAO reduces water's compressibility. In other words, it keeps the water from getting squished under deep ocean water pressure. So we'll keep this one. C, a positive correlation is found between TMAO and the rate at which water's structure compresses as pressure increases. Well, this is kind of the opposite of what we want because the TMAO is reducing the amount that the water gets compressed. C is saying there's a positive correlation. So the more TMAO, the more compression you're going to get. That's the opposite of what we're saying here. And D, analysis of water's molecular structure under high pressure reveals that hydrogen bonds are more stable when TMAO is present than when it's not. Well, that also kind of sounds like it's saying TMAO reduces the compressibility. Now, the difference is that our claim that we're trying to confirm is that the TMAO reduces water's compressibility, not that it reduces its own compressibility. And that's actually the problem with B. B says TMAO's molecular structure shows that it's the TMAO molecules that retain their shape. We don't really care about that. We want the TMAO to help the water retain its shape. And that's what D says. Analysis of the water structure reveals that its hydrogen bonds are more stable when there's TMAO around. So the TMAO is helping the water from getting squished by the high pressure. And the answer here is D.